Hi all, this video is about time series clustering and analysis. So first we are gonna install required libraries. So we are gonna use NumPy and Panda for fundamental data manipulation, and TSLearn which provides us tools for time series clustering and normalization, and sklearn helps with therefore scikit-learn helps with dimensionality reduction, clustering evaluation, and hierarchical clustering. So visualization tools like Matplotlib, Seaborn, and Plotly helps us present results visually. So we're gonna generate synthetic data using random walk blobs from TSLearn library. So this is a great way to stimulate data for clustering tasks. So in our example, the NTS per blob defines the number of time series in each cluster, and N blobs specifies the number of clusters. So after generating 150 time series split across 3 clusters, we also specify a random state for reproducibility. Then after that, we are gonna normalize the time series data. So time series data often has varying scales, making normalization is a crucial pre-processing step. Here we use time series scalar min-max from TSLearn to scale the values of time series between 0 and 1. So normalization ensures that the clustering results are not biased towards time series with larger magnitudes. This step is especially important when using distance-based clustering methods like k-means. So now our data is uniform. We're gonna see how it visually looks like. So we have plot 5 time series samples, each representing a random walk. The reval function flattens the time series for plotting. We also use the alpha parameter to adjust transparency, making overlapping lines easier to look. And then moving on to clustering with k-means. Uh, so instead of traditional Euclidean distance, we use dynamic time warping as the metric. So DTW is ideal for time series data as it accounts for temporal distortions and aligns with time series optimally. Here we define 3 clusters. The n underscore clusters is 3 to match the number of blobs in our synthetic data. So therefore the k-means assigns each time series to one of the clusters. So let's evaluate the clustering performance using a popular metric, Shilloti score. So to measure how well the clustering algorithm performs, we compute this score. So this score measures how similar each time series is to its own cluster compared to other clusters. It ranges from -1 to 1, where values closer to 1 indicate well-separated cluster. In our case, we'll reshape the time series data into 2D array because the score requires flat input. And then after getting the Shilloti score, we're gonna visualize the cluster centroids. So these cluster centroids represent the average pattern of all time series in a cluster. By plotting these centroids, we can understand the key characteristic of each cluster. So we use KM cluster centers to access the centroids. Each centroid is plotted with a thicker line to differentiate it from individual time series. So from the plot, we can see distinct patterns for each cluster. This visualization is particularly useful in interpreting the results of time series clustering. And then moving on to, so these are the various clusters. And then moving on to principal component analysis for dimensionality reduction. So PCA reduces the dimensionality of the data while preserving as much variance as possible. So this helps us plot the clusters in 2D space for easy interruption. We flatten the time series data using a reshape, then apply PCA to reduce it to 2 components. Finally, visualize the clusters using the scatter plot. So this scatter plot shows how the clusters are distributed in the PCI register space. You can see how well separated the clusters are, further validating our results. Then this is the heat map. And then moving on to SACs. So symbolic aggregate approximation. Basically, SACs transforms time series into discrete symbols, reducing complexity while retaining essential patterns. Using SACs to approximate each time series. Visually, the first and transform time series as a heat map. So in the heat map, each row represents a time series in its symbolic form. SAC simplifies data for analyzing and also enabling easier feature extraction. Then moving on to DTW, therefore dynamic time warping. So DTW not only aligns time series optimally, but also computes pairwise distance between them. So let's create a distance matrix using DTW and visualize it using a heat map. So this matrix helps us understand how similar different time series are, which clusters have tighter intra-cluster distances. So the heat map shows pairwise distances. Dark areas represent higher similarity between time series. This visualization is invaluable for debugging clustering results. So then moving on to visualizing hierarchical clustering with dendrons. So another popular clustering technique is hierarchical clustering. Unlike k-means, this method builds a hierarchy of clusters by successfully merging or splitting them. So we are going to visualize using dendrogram, which shows the cluster formation process. So this dendrogram shows how clusters merge at different distances. It provides a visual summary of the cluster process, which can then guide decision like the optimal number of clusters. And then moving on to a TSNE, so distributed stochastic neighbor embedding. Unlike PCA, the TSNE excels at preserving nonlinear relationships in data, making it ideally for visualizing complex time series clusters. So then we apply TSNE and plot the clusters in a 2D space. So the TSNE plots provides a deeper perspective on cluster separation and relationship between individual time series. And then moving on to cluster size distribution. So to understand the distribution of time series across clusters, we plot the cluster sizes. This step is crucial to identify imbalance of imbalance or outliers. So the count the number of time series in each cluster, and so this plot shows whether the clusters are balanced or not. So significant time difference might indicate issues like overlapping or poorly defined clusters. And then moving on to feature importance with random forest. Use the SAX representation to train a random forest classifier, so which assigns feature importance. So this score reveals which time series features are most influential in distinguishing clusters. So this bar plot highlights the features that play key role in clustering. So understanding these features provides insights into patterns driving the cluster. And then moving on to comparing the clustering methods. So these are the autocorrelation of clustering centroids, and as we discussed, this DWD visualizations, and this the mean intra-cluster DW distance between them. So it's the interactive visualization of the various clusters. So the using SAX features, plotting it, the importance of various features, and then moving on to comparing clustering with another algorithm. So we'll compare the performance of k-means with agglomerative clustering using the Shilloti score. So after applying the algorithm, we are going to compute the scores for both the methods and compare the score with uh, bar plot. So these are the results. So the box plot compares clustering quality. So this analysis guides us is one of the best methods for choosing our data set. So thank you.